Hello and welcome to Learn Data. It's great to have you on this channel. In this video, we'll look at the actual implementation of Gaussian process in Python. First, we'll use Numpy library only. So we'll do the coding from scratch, and then we'll use the built-in functions in Scikit-learn to perform the modeling. So let's get into Jupyter Notebook and start coding. Here I've imported these libraries: NumPy, linear algebra, Matplotlib, and this new library sklearn.Gaussian processes. We are importing kernels and Gaussian process regressor. So the very first, let's import those, and those are the versions that I'm using on this machine. So first we'll look at NumPy. So without using any built-in functions from scikit-learn, let's see how we can perform the calculations that we discussed in past two videos. That includes calculating mean, calculating covariance matrices, and the Cholesky um, decomposition of the matrices. So as a first step, we'll calculate prior. So here first we'll create a kernel function that returns a value of a kernel, the def kernel, and that takes in x1, x2, and L. Let's set it to 1.0. Sigma, we'll set it again to 1.0, and then we'll calculate the distance first. So x1 minus x2 transpose, x2 dot transpose, and then we'll square the differences and then use the exponential term. So sigma into np.exp minus d. So this would be similar to a radial basis function. 2 into L and squared L, and that's the function we have. Now we'll set the random seed np.random.seed, and we'll set it to 0. So when we rerun the cell, we get the same output. Set value of n to 50, that's the total number of test samples, test records we have. X underscore test is equal to np.linspace, and we'll create values between -5 and 5. 50 values dot reshape, and we'll reshape it to just one column. And now we can look at x underscore test. So x underscore test, so that's what it looks like. And now we'll calculate the values for prior. So we'll calculate the mean first, which will set it to 0. So np dot zeros x underscore test dot shape. So we have the mean set to 0, and then we'll calculate the covariance matrix. So cov is equal to kernel x underscore test x underscore test. This in the previous lectures, if you remember, this was k star star, and that's what this is. And now we can calculate the prior samples. Prior samples is equal to, now this can be done in two ways, either by using a multivariate underscore normal from NumPy, or we can calculate the L and then do dot products. We'll do both ways. So first we'll straight away use np.random.multivariate underscore normal, because this is intuitively, this is much easier to understand. Reshape -1, and we have C covariance matrix, and we'll get 3 samples. So if we print prior underscore samples dot shape, that's the matrix we have. So we have 3 rows and 50 columns. Now we can plot them. So plt dot plot x underscore test prior underscore samples, will transpose that matrix, and then plt dot axis will specify the axis. So -5 to 5. That's for the x, or we can say plt dot xlim limit. So we have minus 5 to 5, and then plt dot y limit, and that we can set to, I've seen this before, so I know this value should work. And then we plt dot show, and now we can see that this is the plot for prior functions from the prior. We have 3 functions right here. Now what we can do is work on getting the posterior, uh, mean, covariance, and the functions. So let's work on posterior, and this the first we'll try is the one that is without noise, or noise close to 0. And for this we'll get the train value. So x train is equal to np dot array. We'll get 5 data points, -4, -3, -2, -1, and 1. We'll again reshape this to a column, and we can get a y train, and this could be a sinusoidal function based on the x values we have. And so that's what we have for x train and y train. And so with that said, we can now we can also specify the value for noise, which is a very small value, 1 e to the power -8. Now for posterior, we'll calculate all these functions. If you remember from the covariance matrices, or for the joint distributions, we had k, we had k1 star, so that could be this one, and then we have k star star, so that could be this, and then we had, in addition to this, we had k in k transpose as well. So we'll use all of those in this particular scenario. So let's call this k underscore ss, and then k underscore inverse. So the very first one is kernel. We just pass the values for x train and for both the cases, and the noise is 0, so we don't have to worry about anything else. And now for case, the second one is combination of the train and test. So we'll pass kernel x underscore train and x underscore test, and then the one following that is both test, so x underscore test, x underscore test, and then we have k inverse. So this would be np dot linear algebra dot inv and inverse of k. And with that, we can also check the shapes of these. So that print k dot shape, then k underscore s dot capital K underscore s dot shape, k underscore ss dot shape, and k underscore inverse dot shape. And so those are the values for the shapes. Next, we'll calculate the mean and covariance. So for mean, this is posterior mean. We'll save it in variable mu underscore posterior. Post is equal to k underscore s dot t, and we are going to dot that with k underscore inverse, and then dot that with y underscore train. And then for covariance, so mean, so that's the mean we have, and then covariance, we can save it in variable cov underscore post, and we have k underscore ss minus k underscore s dot transpose, then dot that with k inverse, and then dot the resulting one with a underscore s. And these are the same relations that we saw in past two videos that we are using here. And based on this covariance, we can also get the standard deviation. So for getting the standard deviation, we know that variances are the diagonal lines. So we just need to get the diagonal and take a square root of that. So np of diagonal covariance posterior covariance, and then we can take a square root of this. So to get the square root, we simply type np.sqrt, and I'm going to reshape this. Reshape mu underscore post dot shape, and so that gives us the mean and covariance. Now with this information, we can draw samples, posterior samples. So we have our draw samples and posterior underscore samples, and for this we are going to again use np dot random dot multivariate normal, np dot random dot multivariate underscore normal, and mu underscore post dot ravel cov underscore post, and we draw three samples. Let's see. Okay, because I had to restart this, and so maybe I should run all of these again. Okay, so now that we have that, we can create the plots. So plt dot plot x underscore train, y underscore train, and we'll use that marker and size of 8. And then we plt dot plot x underscore test posterior underscore samples dot transpose, and let's why not see the plots as we go. So those are the data points, and then these are the samples that we have, and we can make them dotted by typing that. And next we are going to plot the confidence intervals. So GCA dot fill underscore between, and then we specify first the x test. So np dot squeeze, this is just to reduce the dimensions. So at the moment, if you look at x underscore test dot end dim, it is 2 dimensions and the plot is expecting 1 dimension. So what we can do is reduce the dimensions. So if you type np dot squeeze, that will np dot squeeze, and then look at the end dimension. We sorry, should not be there. So if you look at this, then you get just 1 dimension of that. That's what we are trying to do here. The next one is np dot squeeze. Here we have mu underscore post minus the plus minus standard deviation. So mean, this is minus standard deviation, and then we are going to have mean plus standard deviation. Np dot squeeze mu underscore post plus 2 times standard deviation, and finally you can set the color. So I'm setting this to a very light blue, that's Alice blue color, and now we can try and print this. So my mistake there, fill between, and as you can see, we can see a nice shaded area there. So wherever we have data points, the uncertainty is low, and so the confidence margin is much lower. But as we go in this area where there are no data points, we see there is a very big confidence margin. We can we can also plot x test also on this, x test and mu post. So plt dot plot x underscore test, and then plot the means for that, mu underscore posterior means. And then we can set the plt dot x limit. So x limit we can set this to minus 5 by 5, and then plt dot y limit, let's set it to minus 3 by 3, and we can look at the plot. And this is the final plot we have. As we can see, that's the prediction line, and these are the confidence limits, and these are the functions that we have from the Gaussian process. So that's one way to uh, perform the Gaussian, to look at the Gaussian process using uh, data that does not have any noise. So posterior using L and Cholesky, will not use any noise here in decomposition. So np.random.seed, we will set it to 0. So n is equal to 50. Now for data, we have x underscore, we'll use the same data. So why don't we go ahead and copy all that? So this is the same data we'll use, and I'll copy and paste that here. We don't need the noise, so I'll remove that. And for x test, again is the same stuff. np.linear_space linspace minus 5 to 5, 50, and reshape this to minus 1 and 1. And capital N, which we'll use later on, we'll set it to the size of x train. That's the number of training points. And now we'll perform the train. So for training, we first create the kernel, k kernel, and it's the same kernel that we have up above, x train, and then again x train. So that gives us the kernel. And with this kernel now, so if you look at the shape, or we'll see, that's the kernel we have. Look at the print k dot shape. We have 5 by 5 kernel. We can get the L kernel out of that. So L is equal to np dot linear algebra dot Cholesky and k. So with this, we have the L, and we can use this to calculate the mean. So mu is equal to np dot ls. Sorry, uh, we need another kernel before we can do that. So test mean, we need the ks. So kernel x underscore train x underscore test, and then we calculate again the L value with the Cholesky decompose. No, here we'll use the solve, np.linearalgebra.solve, and we have L and ks. So we use those two, and then use that value to calculate the mean. So for mean, we'll first solve set of equations, linearalgebra.solve. We'll solve L and y train, and then with the output of that, we'll dot np dot we'll dot that with ls transpose, and that will give us the mu. So we have the mean, and similarly we can now get the variance. And for variance, we again need another kernel, kss. So kernel x underscore test x underscore test again, and we can get the standard deviation. SD is equal to np dot diagonal k, capital KSS, and we are going to subtract KSS, and we are going to subtract np dot sum ls squared, my axis is equal to 0, and then take the square root of that. So we have this, and then np dot square root, then do the reshape with which has the same shape as mu. We have the test mean and test variance there. So next we can calculate the test posterior value. So we are going to do the samples, and for this again we'll calculate the value of L is equal to np dot linear algebra dot Cholesky, and we use KSS plus 1 e to the power minus 6 star np dot I n, and minus, we subtract the dot product of ls transpose ls dot t and ls. So once we have this, we can calculate the posterior samples, which is equal to mu dot reshape minus 1 1 plus np dot L, and here we can use a random normal. So previous cases we have used the multivariate, so here we are going to use random normal. Random dot normal, and size is equal to n comma 3. So with this is a double L. So with this we can now create the plots. For plotting we have the same setup as before, so we'll copy the same code and paste it here. So we have X train, Y train, everything else stays the same. Instead here, instead of mu post, we just need to type mu, and the same thing here. We are because we are calling this as mu. And so we have X train, Y train, X test posterior samples, and in p dot squeeze, and this should work. So let's see, must have X and first term must have the same dimension. So here maybe we don't need the transpose in this case. So as you can see, we get output that is not exactly the same curve as what we had before, but we see different functions that we have sampled from the posterior, which are shown by dotted line. We have the prediction, and again the trend is same, that where we have the data points, the confidence intervals are much narrower, and they kind of they are pinned to the data point, and in the regions of uncertainty where there is no data, the width of those bands is much larger. Now let's look at how we can use the methods in scikit-learn to perform Gaussian process regression. Scikit-learn, and here we already have imported the libraries, so we'll get started with writing the code. np.random.seed, we'll set the seed to 0, n is equal to 50, so those are the number of data points. And as in previous project videos, to run all the possible kernels, we'll create a list of kernels. So kernels is equal to kernels.rbf, and we'll leave the values as default in this run. So kernels dot let me copy this because we will be typing that several times. RationalQuadratic, and then we have kernels dot exponential sine squared, and here we'll specify the periodicity. to 10.0, and again kernels dot product, and here we'll specify the value for sigma underscore 0 is equal to 1.0, and we'll square that. And finally we have kernels dot Matern, I think, which is that. And now we'll iterate through all of these. So we'll create the first, calculate the prior, and then posterior, and we'll plot each of those as they are calculated. So for kernels, for kernel in kernels, so first we'll specify the Gaussian. So Gaussian process. So for this, we'll initialize this with GP is equal to, or GPR, either way, Gaussian process regressor, and here kernel is equal to kernel. It's this kernel that we are using and not the custom kernel that we had mentioned earlier. And then we have for prior, x underscore test is equal to np dot linspace. Let's go from -5 to 5 and have those 50 data points there. We reshape this from -1 to just one column, and then we'll calculate the mean and standard deviation. Mu underscore prior is equal to mu underscore prior and mu underscore standard deviation. Sorry, standard deviation underscore prior is equal to gp dot predict x underscore test return underscore standard deviation is equal to true, and then we can sample. So samples from prior is equal to gp dot sample underscore y x underscore test, and we need 3 samples, so we'll just have 3 there. So with this we can print what values were used, what kernel was used. So we can do that here. Print, this is just a line for separation, into 50. So we'll print 50 asterisk, sorry, pound signs. Print kernel, so we'll know which kernel was used, and then again just a separating line here. With that, we can now create the first plot. So plot plt dot figure and fig size. We are creating subplots side by side. So we are going to create a figure size here 10 by 3, and then plt dot subplot. This is the first plot, so 1 comma 2 comma 1, and here we have plt dot plot x underscore test mu underscore prior, and so with that we can also now fill that. And so plt dot fill between, so this would be between x test and the mean and standard deviation for the prior that we have calculated above. So x underscore test dot ravel, and every time you see me type this ravel or reshape, this is just to get the arrays or matrices in specific formats, either a column or a row. That's all there is to that. Mu underscore prior minus sd underscore prior, and then mu underscore prior plus sd underscore prior, and then color will stick with the same color, Alice blue. Okay, so with the confidence bands in place, we can finally plot these sample functions. plt.plot x test samples underscore prior, and we have these two. So we can run this and see how they look so far. Okay, so that should be commented. And kernels.rbf. So what am I missing? List has no attribute rbf. So line number 5, list has no attribute rbf. So we have kernels. So why don't I go up and run this again? Run that and go back up here. Run this. And now we have another error. Fix size. Spelling mistake probably there. Yes. And another list has no attribute rbf. So let me copy paste the library again here, and I'm going to change this name of variable to underscore and run these two and name mu. Okay, so that's my mistake. Prior, which is right here. Okay, so that seems to work. Okay, so with that, now we can move to fitting the Gaussian. So we can do the fit, and for fit we have x underscore train is equal to np dot array, and we have the data points -4, -3, -2, same as what we had before. And I'm going to reshape this to a column -1 by 1. And after this we have the y train, which is going to be the sine function. Y train is equal to np dot sine x train, and we then can fit on this. So gp dot fit x underscore train y underscore train, and with that we can now get the uh, posterior. So for posterior we can calculate the mean mu post and then standard deviation for post, and this is so that we can create, while plotting we can get the confidence interval bands or plus minus standard deviation bands. gp dot predict x underscore test return underscore standard deviation is equal to true, and we can reshape the mu post so that we can plot it. Mu underscore post is equal to mu underscore post dot reshape. And if you're wondering how I know that we need to reshape this, and that's because I've tried this before, and uh, you'll get an error if you do not reshape it, and so you will figure out that the shape has to be in that specific um, order, and so that's why I'm doing it ahead of time. And then for np, so for sample post we can get gp dot sample underscore y, so x underscore test, again we get just 3 samples, and for this we need to reduce dimension np dot squeeze, so I'm using np dot squeeze there. And finally we are ready for the plot. So for plotting, because we are going to have more or less the same code, I'm going to copy what we had earlier. So copy that and paste it here, and do a couple of changes. We don't need that line, and this is going to be the second plot, so we are 2 there. This is going to be mu post because we are talking about posterior, and then fill between x test ravel, and this is going to be again mu post instead of prior. So let me change that. And then the second is going to be standard deviation also for the posterior, so we'll change that. Color I will leave it as is. Then x test sample Again, this is going to be the posterior, so we change that, and then we'll have the data points in the scatter x underscore train y underscore train comma c is equal to color is equal to blue. So color is equal to blue, and let's set the size of these to be 50. And finally, we can label this one. Earlier one we did not say label, so let's go ahead and do that. Plt.title, this is going to be the prior, and this is going to be plt.title posterior. Okay, and we can look at all the both the plots. Plt.show, and before we end the loop, we can print and look at the kernel and the log marginal likelihood values. The print gp underscore gp dot kernel underscore, and here we can type gp dot kernel underscore, and then we have print for likelihood gp dot log underscore marginal underscore likelihood, and that again gp dot log underscore marginal underscore likelihood gp dot kernel underscore dot theta. And I'll get to a minute how we can find what to type there. Print, and here we have, let's plot 50 lines, hyphens to separate, and add some blank rows there. \n, and now when we run this, we get an error. So samples underscore post is not there. That is correct. We have sample. We could add an s here or remove s there. And then plot is not defined. That's correct because it has to be plt.plot. And another scatters. Okay, another one. Okay, plt.scatters. Okay, so has no attribute gp underscore kernel. Oh, that should be a dot there. Okay, so finally we have the plots. As you can see, so here the very first one, this is the rbf kernel. We have length scale of 1, and this is the prior. On the right hand side we have the posterior, and we have the log marginal likelihood values down there. And we can see that again here there is a tight fit on the right hand side, where there are no data points, the fit changes drastically. Again the same thing here, we have prior and we have the posterior, and these are another set of functions. Again we have some here. We have the likelihood is the same, around -3.4 for all of these. And then this fit is something that is completely different than what we had above. This is the dot product, and it does not seem to capture the sinusoidal shape of the data that we are trying to get at. And this final, we have the Matern or Matern, which does seem to capture the shape as we are trying to do. Now, while we are doing this, if you are curious how linear regression would work, so check how that would look like. Linear regression, and we'll use a polynomial. So this is digressing from Gaussian process, but uh, just to take a look at what to expect from Scikit-learn, import linear underscore model, from Scikit-learn, import pre-processing, Scikit-learn. Okay, So here we'll use the same data. So I'm going to copy the exact same data, which is for the train. That's right here, and also for the test. So that's the train, and for test we have this line right here, and that should do it. So we have those three lines, and okay. So here we now have the X train and Y train. N again is the same in, I think it was 50. So first thing that we'll do is create polynomial features, because we know that this is not linear. A straight line is not going to work, and so we'll do pre-processing dot polynomial features, and we'll use a degree of 3 should suffice. Then poly dot fit x underscore train, and then we'll create x underscore train poly. That's a new set of features, poly dot transform x underscore train, and the same thing we'll do is transform our test. So change that, put a test there, change that, put a test there with just 1t. Okay, so that's a new data. Now we can model. So for model, we'll use the linear model, linear underscore model dot linear regression, and reg dot fit. We have x underscore train underscore poly, because that's what we need to use, y underscore train, and then we are going to get the ypred is equal to reg dot predict. We'll predict this on the test underscore poly, and with that we are now ready to plot this. So figure is equal to plt dot figure fig size, and I'm trying to get the same size as what we had plotted above, so rectangular shape. Now plt dot scatter x underscore train, y underscore train, color is the same blue, and size is the same 50. And then we have plt dot plot x underscore test, y underscore pred. Those are the predictions, and we can set the limit. X limit is going from minus 5 to 5, and for y lim, because we'll set it at minus 3 by 3 first. So minus 3 by 3 and see how it looks. So plt dot titles, this is going to be linear regression, and we can now look at the plot. Plt dot show. So this is how our plot looks like, and as you can see, it doesn't show a sign of turning back down. So I'm going to change this and go uh, maybe not for x but for y. So this was supposed to be y. uh, okay, that didn't work. So why don't we do this, change the value of y to maybe minus 1.5, and it goes right up to 10. Okay, so that's the plot we get. As you can see, the Gaussian process was able to capture the hidden sinusoidal function in the data, whereas just linear regression is not able to do that. For linear regression, we just get this looks like a fit that is just one curve, and that's similar to this dot product kernel that we had used earlier. So they are pretty close. However, the very powerful feature with this Gaussian process type of model fitting is that it is able to capture hidden trends within the data, even in presence of noise. And this was a toy example where we looked at a very small data set, but in the next video we'll look at one real world example in a project where we'll use the Gaussian process to find the trends in the data. So that was it for this video. Then I hope you enjoyed this video and found this video helpful to understand the Gaussian process implementation from scratch, and also by using the Gaussian process regressor from Scikit-learn. In next video, we'll look at how to use this on a real world project. I think we are going to try the CO2 prediction project from the Scikit-learn docs, and I also have found some data on online, and we can use that as well to predict greenhouse gases. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.